In this recording, we will extend the energy balance to the operation of a batch reactor. A batch reactor has constant charge and constant discharge. No steady flows of incoming and outgoing streams exist in the operation of a batch reactor. As a result, the species conservation equation for a batch reactor reduces to dNA over dt is equal to Ra times V. Again, we are discussing this for a hypothetical A goes to products type of a reaction. This is the species conservation equation. The energy balance, on the other hand, reduces to du over dt is equal to, this time we have heat interaction in the reactor and we have shaft work and we might have surface boundary movement, P dV over dt. This is the first law reduced to a batch system. The necessity of the P dV term makes itself more relevant, especially for systems like an engine cylinder. All right, now we are going to, again, generate a stoichiometric table. This time our hypothetical reaction is going to be, again, A times A plus B times B, producing P times P plus R times R. And our reduced stoichiometric coefficient representation of the same reaction is A plus B over A times B going to P over A times P plus R over A times R. Now there are no inlets, no effluents in this reactor. But again, we have to write a stoichiometric table to be precise in our derivations. So our species are A, B, P, and R. Initially, we have an A0, and B0, and P0, and NR0. And we are going to represent these in terms of their ratio with respect to Na0. As we have done in the previous case, we are going to have this as Na0 times theta B. This is going to be MP0 times theta B. This is going to be Na0 times theta P and A0 times theta P. This is going to be Na0 times theta R. Initial ratios. And of course, you're going to have a change. And the change is going to be Na0 times X. X is the conversion. The change is going to be B over A times Na0X. The change will be minus P over A times, actually, these were going to be minuses, and this is going to be plus P over A times Na0X. And this is going to be R over A times Na0X. We're going to use these in deriving the energy balance. All right. Now, as far as this part is concerned, we are fairly clear now how we can use this. We have solved an example. We're going to frame this and we will continue with the energy balance. Let us work on this term, du over dt. What is du over dt for a reacting system? It is d over dt times summation of all the species and I times ui. This is the internal energy. We're going to take the derivative of this. This is going to be summation of d and I times ui plus summation of ni times dui. Internal energy of species I, number of moles of species I. And as far as our reaction is concerned, we have species I, A as A, B, P, and R. Now let's see. D and I. What is it? Is d of ni. It is d of ni0 plus nu I over nu A times Na0 x. So if we clarify this for a sample species, say for example D and P, this is D of NP0 plus minus nu I is P, nu A is minus A, therefore we have minus times Na0 x. This is a constant. It drops out of the equation and dNP becomes minus P over A Na0 times dx. Okay. So dni is equal to, in its most general form, nu I over nu A, the principal stoichiometric coefficient of the principal species. In this case, it is A times Na0 times dx. What is dui? dui is C sub V times dt. This is the constant volume heat capacity. This is the temperature in absolute scale. So we collect them together to obtain du over dt to be equal to u sub I times dni summation over all species u sub I times dni, which is nu I over nu A times Na0 times dx. And the second term, plus summation of Ni times dui. This is our basis which we will use to derive a general balance equation for batch reactors. General energy balance. Let's continue. Let us substitute Ni from here. Ni is equal to Na0 theta I plus nu I over nu A times X. We're going to regroup the first term. We're going to take the ones that are independent of the species outside the summation sign and continue. Du over dt is equal to Na0 dx summation overall components, overall species, nu I over nu A times ui plus the second term, Ni, Na0 theta I Na0 times theta I plus nu I over nu A times X times dui. Okay. Let us define our expressions. If we remember from our previous recording, from the enthalpy side, a similar term has appeared in our equations. This term we identified as minus delta H of reaction. This term is now our minus delta U of reaction. So our expression is becoming more compact. Let us apply the same analogy here. We have in this term, let us expand this term only, summation of Na0 summation of theta I times dui plus Na0x summation of nu I over nu A times dui. And if this is delta U of reaction, we are going to come up with a similar explanation for this term. Now we continue. I have transferred the expressions that I have derived here right underneath the du over dt term. We have du over dt comprised of three terms. The first term is Na0 dx times minus delta U of reaction. The second term is Na0x summation over nu I over nu A dui. And the third term is Na0 summation of theta I times dui. This term has a striking similarity to this term. So if I just take these inside the derivative sign, I obtain d minus delta U reaction. All right? dx over dt, we have to be precise, d over dt, dui over dt. All right? So this crowded domain looks like this. du over dt is equal to Na0 d over dt x times minus delta U reaction. I have combined these two terms. These two terms can be combined as such, plus Na0 summation of theta I dui over dt. So this is the most general form of the internal energy term of the reduced first law expression for a batch reactor. Now we continue with a more cleaned up space. We have du over dt expressed in terms of the delta U of reaction, the stoichiometric ratios of the feeds, and no, there's no x here, sorry. There is no x here. And then A0. All right. Now we are going to substitute for dui over dt as a Cv dt over dt in order to have a more compact expression of du over dt as Na0 d over dt x minus delta U reaction plus Na0 sigma theta I dui over dt is going to substitute from here times Cvi dt over dt. Now this term can be taken out here. It is common for all the species, and we are left with a term called theta I Cvi. So theta I is the feed stoichiometric ratio, Cvi is the constant volume heat capacity of species I. This is going to be the average heat capacity of the feed. So in its most compact form, du over dt term reduces to Na0 d over dt x minus delta U reaction plus Na0 mean heat capacity of the feed times dT over dt. This is the first part. The right-hand side of the equation is equal to Q plus shaft work minus P dV over dt. This term, dV over dt term, can also go through the same kind of algebra as this term, du over dt. To begin, I will write the first step, and I will expect you to complete the rest. This is going to be du over dt summation of all the species Ni times Vi. Just like we have started from du over dt as the summation of Ni times Ui, this starts as du over dt summation Ni dot Vi. Please follow and finish this derivation for the V term.